Well, hello, everybody. Thanks for joining the webinar so far. Good morning, good afternoon, good evening. I know out here it is snowing in the afternoon, so that's making it an exciting day. But appreciate everyone joining in on this webinar. My name is Brian Benish with DSIAC, and I'm just going to give a quick introduction to our organization, just to familiarize everyone with who we are, what we do, and why we're hosting this webinar, and then quickly hand the mic off, so to speak, to Emma for her presentation. So just quickly for who we are as an organization, DSIAC, we are the Defense Systems Information Analysis Center, DSIAC. We are a DoD entity operating under DTIC, the Defense Technical Information Center. And ultimately, we're here to support the DoD research engineering community by conducting information research on technical topics. So we have a wide range of technical folks on staff with us who are here to help you find information you might need on any defense systems related topic that you're doing DoD research engineering on. And so we do that research ultimately to help facilitate some sort of collaborative opportunities so that if there are others working on similar projects throughout the DoD community, we can help maybe connect you to them. We want to help find information that's related to what you're working on so that you're not going to repeat efforts that have already been done in the past or maybe are ongoing at the time. And we want to stimulate some innovation, some new ideas that are out there. And so to that end, we also host these webinars as a means of pushing out information, creating an awareness of what is being done in the DoD research engineering community at large, so that, again, work is better understood. There's no repeat work being done. And then there's opportunities for collaboration. So I'm very excited to have Emma here to give her presentation about what they're working on. We hope that you find some great value out of what's being presented here. And just a real quick introduction now to the logistics of the webinar. If you are joining in via the web platform of it, you'll notice a little chat bubble at the top of the screen where it should say view audience questions if you hovered over it. What that'll allow you to do is anytime during the presentation, you can click that, you can enter your question, and that'll put it in queue so that when we get to the Q&A portion at the end, we will go through those questions one at a time as they're received. So I would encourage you at any time during the presentation or after, of course, to submit your questions that way. If you were just simply dialed in and listening to this, you can head to the DSIAC website where this webinar is posted, and we should have PDF slides available for you to download to kind of follow along as best you can. I do apologize that unfortunately, just by the nature of what we're doing here, you're not able to ask questions audibly. So if you're simply over the phone, you can follow along. If you do have any technical issues, that is a backup. You can just simply dial in and download those slides. And then finally, note that we are recording this. So if you have any persistent technical issues, this will be available afterwards for you to watch. We'll put it on our YouTube page. I think we'll try to get it on our Facebook page and a couple other places we'll share it out. Okay, so that I think covers everything that I wanted to mention about this. So without any further ado, Emma, I will hand the mic over to you for the presentation.
All right. Well, thank you so much, Brian. I really appreciate it. First, I want to thank the DSIAC to give us this opportunity to present the webinar to everyone, and thank you all for joining us, taking the time. So hopefully this is informative and educational as well. My name is Emma Morgenstern. I'm a project manager from Align Science and Technology. I've been with Align for about 5 years now, and this is actually my second tour, but I started as a software engineer about 17 years ago and gradually grew into project management with the focus of in web application. So today, my colleagues from the Viper team and I put this presentation together, and we'd like to introduce you to the vision of the next generation propagation tool. So let's jump right into it. Okay, so today's webinar tells a story of how we came to our vision for the next generation propagation tool, given the needs and challenges of today's network planning. And then we'll talk about the vision for the next generation propagation tool, and then go over the technologies and theories that we explored, and as well go behind the science for math and physics behind the tool as well, and wrap it up with a quick demo to showcase the speed. Okay, before I jump into the juicy technical details, I'd like to actually talk about the needs and challenges in the network planning today. And I want to talk about in the following aspects, which is the flexibility, accuracy, speed, and of course to support the 5G deployment. Okay, so I know some of you are the RF SMEs in the audience, so you know exactly what I'm talking about when I say urban clutter, urban canning. But just bear with me because I want to paint a full picture of the problem we're trying to solve for the rest of the audience. So just bear with me. So urban clutter, think of a big city like New York City. You have skyscrapers and then you have small buildings. And they're surrounded by skyscrapers that creates urban canning and creates challenging and flexibility that you need things like post-site analysis. Now, in today's existing propagation tool, one thing that's worth mentioning is bridges. For example, the space under the bridges is not always taken into consideration. As a matter of fact, by the existing tool is treated as a concrete wall. That creates challenges. Complex indoor networks. Well, we all know in the office you have many devices ranging from desktops to handheld devices, tablets, you name it, and that creates a challenge in flexibility because it's so complex. Rural area. So outside of urban, you still have different terrains that you have to actually take into consideration, like mountains, caves, ocean, forests, etc. Okay, buildings and environmental materials. So in today's existing propagation tool, the building materials is not always taken into consideration. As a matter of fact, it's treated as concrete all the time. So, but in reality, like skyscrapers, in big city, they're made of glass. So when that's not taken into consideration, you create challenge in accuracy. So concrete, glass, any building materials, and environmental materials such as trees and foliage as well. Weather. So we have rain, snow, and dust, and fog, and that's just part of a reality in real life. But some of the existing tool doesn't always take the weather into consideration. Is always considered this is just sunny, and that's not very accurate. It would be nice to get stats from past and have a real life weather feed from NOAA.gov that gives the locations and rates of either snow or rain, etc. Okay, needs and speed. This probably ranked the highest desired item in all the needs and challenges. Some of you from the audience today know exactly what I'm talking about because this is your current struggle. Due to the slow rendering, some of you probably kick off loading elevation data, and then you have to go away for days to come back to get your result. And that is very cumbersome. In today's, modern life, everything comes faster with a smartphone. So in network planning, propagation tool, a true full 3D modeling in near real time is definitely highly desired. Okay, this is just a quick overview of the limitation of existing tools we have. So you have some tools here that doesn't address 3D modeling. It's not a 3D modeling tool. And it doesn't take building materials or environmental materials into consideration. And it doesn't have true wedge diffraction, maybe knife diffraction, but not a true wedge diffraction. And then the other tools that doesn't cover the full range of frequency range, nor does it take weather into consideration. So what do you do when you know what you need and want? So I want to share a secret in life. Dare to dream. Everything starts with a vision. So align with our RF's needs and all the experience we had obtained in supporting our DoD customers over the past 60 years, we know what the next generation propagation tool needs to be. It needs to replace the legacy tools to better predict signal loss in accuracy and in full 3D dissimulation. This GPU-based propagation modeling tool is capable of efficiently simulating complex wave interactions such as wedge diffraction, curved surface diffraction, etc. It implements a wide range of frequency use, including low, mid, high, and it will have millimeter wave path analysis, enables micro cell and picocell deployments. It leverages beamforming and phase array technologies, and as well as massive input, massive output technology as well. It is a full 3D modeling and it's GPU based, which considers building materials, clutter geometry, as a real life weather feed, does wedge diffraction, surface diffraction, and reflection. And it leverages volumetric and voxelization, which I will go into details in a minute here. And it uses ray tracing to do the rendering. So with our RF expertise, we can address complex clutter, dense urban deployments, site analysis that I mentioned earlier, as well as interference avoidance analysis. It does line of sight and beyond line of sight calculations, as well as aggregate coverage from multiple locations. It is a true 3D modeling in near real time, runs at a revolutionary speed that possibly is 3,000 times faster, and I'll show you that in a minute. And it supports 5G deployment. So with that vision in mind, we explored the following technologies and theories, and I'll go into details for each one of them. Okay, volumetric. So how do we achieve full 3D modeling? We have to figure out how to dissect a 3D space. So the tool does not just merely calculate receive power along from A to B, but calculates the entire volume filled by RF field inside a 3D space. So we've leveraged something called Voxel, a volumetric geometry representation that is a 3D volumetric model that composed of these voxel elements. So think of it as the equivalent of a pixel in a 2D digital image. It is just in a 3D space. Okay, so we dissected the 3D space. So how do we take buildings and environmental materials into consideration? We leverage something called voxelization. So we have to figure out how to store these data. So each voxel contains attributes of its bounded space, and it stores data like surface normals and geometric hints, reference the material it contains, and the physical properties of that material. But this quickly becomes very expensive and impractical. So how do we be efficient with 3D modeling and with all the information it stores? We overcome this difficulty by using something called single large voxel. What that means is anytime there for the open air spaces, buildings, mountain ranges with the same characteristics, we treat it as one big large voxel. And it stores with material and location data with it. And on the edge of these 3D spaces, there are smaller voxels that has more geometry and material data. So we envision the next generation propagation tool to use a tree hierarchy called octree to organize this division. It allows the tool to deal with very large models efficiently. Okay, so we dissected 3D space, stored data. So how do we chain everything together and still stay efficient? And this is where we leverage the sparse voxel tree, which is an extension of the octree, a very compact pointer-based structure. It's sparse is because all the node that with the same characteristics is not subdivided. So if you look on the right-hand side with the picture, the glass building is not divided for sections that has the same exact characteristics. Same thing for this building with the yellow outline. So that's how we actually stay efficient. And but at the same time, all the details of the object always belong to back up to a main node, and you can store the the data with minimum redundancy, but still trace back to everything and chain them together. So the benefit of the sparse voxel tree is speed, because you don't have to investigate every voxel within the system. Okay, so we can do 3D modeling efficiently, but how can we make sure it looks still realistic? And this is where the ray tracing comes in. So ray tracing is just another way of drawing a 3D picture, but it's fundamentally different than rasterization, which the gaming industry leverage. Ray tracing it simulates the real light more accurately because it describes where it actually gone through and not just a guesswork. So as you can see, it's on the pictures on the side, it's a little bit subtle, but I can point it out to you. If you look at the right-hand side picture, it's very realistic, just gentle, simulates the real light. Instead of left one, it's very actually kind of bulky looking, right? So it's more realistic if you use ray tracing. And the fun fact is, actually, ray tracing is not that new. The film industry had actually leveraged for a long time, but using a offline render farm. But that is something that gaming industry cannot actually do because it needs render in real time. So how do we overcome gaming industry's problem? We use GPU. So GPU-based parallel computation gives us high speed, and it turns a laptop into a supercomputer. So although ray tracing is not new, but the hardware with NVIDIA chip that has a ray tracing package is fairly new. As you can see, the RTX 3000 just came out about 2-3 months ago, so that's fairly new. Okay, putting everything together. So this is where I want to share the second secret in life. Do it. So at Align, we practice what we preach. Now we know what's needed and what's wanted. We combine all the technologies and theories and hardware into one innovative approach and created Viper. It stands for Volumetric Integrative Propagation Engine for Ray Tracing. Viper integrates terrain-based analysis and fully 3D environmental characteristics, including real-world building geometry and materials. So the next part of the webinar is the science behind Viper. And I'd like to introduce our very own scientist behind Viper, Dr. Edward Smith Rowland, who will take you through the fun part of the math and physics behind Viper. Doctor, the floor is all yours.
All right, thank you very much. Okay, so next slide. Okay, here we've talked about the representation of the geometry that we're working with now. We're reorganizing our models to leverage the massively parallel GPU architectures available now. So basically, we're recoding a lot of our models as compute shaders and run them to be run on the GPU. We're also moving, as we've talked about earlier, from faceted or wireframe geometries to this voxelized description of the surface. This allows us to leverage the fast ray tracing. You know, the voxelized geometry allows fast geometry traversal. It also gets us past the struggles of repairing faceted models and wire models. You can do constructive solid geometry with voxelized geometry and repair models kind of implicitly. Basically the model repair game doesn't scale when you're trying to cover a large urban area or large amounts of terrain. Okay, let's see. This is just, I'm just going through sort of the top high-level architecture. We're using the uniform theory of diffraction for our electromagnetics. And also maybe we're looking at sort of the cousins of UTD as well, the incremental length diffraction coefficients, which basically turn the UTD functions into green functions, that allow you to integrate currents that you drive over in the scenario. This has proven very useful for us and very effective in some of our other models. ARAP, which is an aircraft propagation model, for example. And you've probably dealt with NEC-BSC, probably some of you. That's a good solid model. Also, we need to be able to feed these models. And for that, we need, among other things, a materials database. You need to have the electromagnetic properties of materials over a wide range of frequencies, from HF on well into millimeter and terahertz range if you can get it. And we're maintaining a database of a lot of building materials, airframe materials, and we're always adding to that. We also have semi-analytic models like coal and some others. And we also need antenna databases and the ability to read things like industry standard gain patterns, and treat, a wide range of horn and antenna and aperture antennas. And finally, Alliant has a huge database of raster and LiDAR data covering the globe at high precision. And we have a group of people who dedicated to maintaining this library and making sure that, that it has integrity. Okay, next slide. Okay, some of you, I'm sure you've seen this. This is just an example of a UTD diffraction coefficient. It accounts for basically the ability of electromagnetic energy to bend around corners or creep along. Oh, apologize for that. Hold on. Sorry, we have a guest. Hold on.
It's part of the nature of working from home nowadays.
Yeah. Sorry, a guest speaker.
No worries.
Okay. So anyway, we treat wedge diffraction with materials. We treat surface creeping ray mechanisms. Reflection, of course, with materials. And we have multiple, in a given path, you'll have several of these mechanisms happening in sequence, and we need to accumulate the effect of these things at the final receiver. Okay, next slide. Okay, here's just a simple 3D representation of what happens in wedge diffraction. You have the green transmitter on the far side of that metallic wedge, and you see how the ray comes from that transmitter up to a diffraction point along the edge. And for that ray, incoming ray, the wedge diffraction causes a cone of spray sort of to happen. So you have significant field diffracted from that point along on the surface of that cone. And here you have the receiver down there in red receiving that signal around the corner of that wedge. And for those, I'm sure some of you have seen the Keller cone, people who have done UTD before. But that's just a illustration that is nice to see. So let's go to the next slide. Oh, okay. So here what you get is electric and magnetic fields, which are continuous for a given transmitter as you go through the scene and as you cross through shadow boundaries. Where you cross from where optically an object, a receiver would become invisible as it goes behind a building, you have continuous field. You do have field behind there. So the UTD theory gives you nice continuous fields everywhere. And that's just an illustration of the numbers that come out of that cone thing that I showed you before. Okay. All right. We can go on. Next slide is just more materials database. Okay. Here we have the electric permittivity, magnetic permeability coming, from a tenth of 100 megahertz up to a terahertz, ideally. It can be difficult to scrounge that up, but we've done a pretty good job of doing that for a lot of building materials, soil, weather-related materials, water, seawater at various salinities, temperatures. We have sub-ram coatings for airframes. A lot of building materials like brick and cement, soil in various conditions, stuff like that. And you need to have all this in a way that you can immediately feed and populate your scenario. You need to be able to assign these materials to the surfaces in your model. And we have fairly robust things to do that. And often the LiDAR will come with some radiance measurement where you can use that as a proxy to detect when you're off of brick or glass or soil. Okay, let's move on. Next slide, please. Okay, antenna-based database. A lot of gain patterns. We store, two-cut patterns, full 3D patterns. Generally, a user will come into a problem with a wide range of levels of information. At the low end, somebody might just have a full gain, main beam gain at one frequency, all the way through gain patterns and gain patterns with polarization, all the way down to aperture fields and currents. So we need to be able to ingest that wide range and give the user the best answer that we can. Okay, and once you know, one of the major use cases of models is you have, you know, a canned antenna model, but you need to understand how that antenna actually behaves when it's installed on a platform or in an environment. So you want to calculate the effective gain pattern from the one you get out of a book or from, you know, the spec sheet. How does that, what happens to that when you put it on a platform, a tank, for example, down there, or on the back, you know, on an airframe, which is the line plot shows you something that would have been a nice dipole. What happens when you put that, or a monopole rather, when you put that on the top of an F-16, for example. Okay, next slide. Okay, our platform and geographic database, we have tons of LiDAR, down to sub-millimeter, KML, gray polygon buildings, raster formats, you know, raster files. We also have triangulated and wire models of a lot of airframes and ships. A lot of the military, U.S. military catalog is in that. And we have access to that in this model. Okay, next slide. Environmental data. Okay, we of course have access to the ITU statistical data for rain, snow, fog. We're looking at integration with weather services, either for real time or for just site-specific statistical information. Also, of course, we have propagation models to go with that. You know, ITU models does a lot of the rain fog propagation. We have Me-series models and higher frequency models to just take, if you want just a pure particulate scattering model. And we integrate these all into our models, into Viper. Next slide. Where am I? Is that it? Okay, demo. Okay. Okay, here you see a map of Norfolk, Virginia. White is the highest elevation, black is the lowest. You see, we're going to be talking about some of the structures here, the bridges you go, especially the one going across the, here it's pointing to the building. There's a tall building there in white at the big rectangle. You've got two bridges up top and one down below here. Okay. Now what we're going to do is put an antenna right on top of that rectangle building. Boom. There's your bug splat plot of gain. You see the orange is the regions of highest gain. And I'm having help here. I apologize. And you see the shadow of going around the building. The blue, dark blue, is the high loss, low gain area. And you see, okay, here we're going to go, now we're going down the river. That shows you how fast the model recalculates. That's a real moving of mouse and recalculating. Here we're going to do the same thing on the low river. And you see the effect of the bridge down there. You see the shadowing of it. The transmitter and the antenna are at the same altitude right now. But we're going to treat that. Now we have one, one is below the antenna bridge level and one is above, and you see propagation under the bridge. Okay, that's the end of the demo, and thank you. I'm going to mute right now, and I'll look for questions.
Thank you, Ed. Thank you, Ed. I really appreciate it. Just real quick, that is actually just wanted to showcase the speed, because I know I said something earlier that you know, this tool can possibly run 3,000 times faster. And what you saw there is actually a 1.5 kilometer by 1.5 kilometer, a 2.5 meter tile. So it's a 600 by 600, and that gives you about 360,000 probe points. So this actually takes about 15 minutes in the existing propagation tool, but in Viper it takes 0.3 seconds, just like you saw what Ed was just showing you. It's near real time as you moving the mouse. It's recalculating everything, and it's, if you do the math, it's about 3,000 times faster. We can, I mean, I know it's very short because the frame rate is hard for us to show you everything, but we'll be more than happy to show you, you know, a demo that's more applicable to you. And you can actually contact me or my colleague Jen Super, and we can actually work with you and give you a demo that's, you know, more that's actually applied to your use case. Okay. So Brian, I guess before I hand this over to you for Q&A, I'd like to bring my program manager, Matt Neidig, into the discussion for any questions. But at this point, I'm pretty much done with the slides. You still there, Brian?
Yep. Sorry about that. My computer just
Okay.
Okay. Yeah.
Do you want me to stop sharing here, or?
No, you know what? I'm going to jump right into the Q&A. So you can just sit tight and see if we can do this. Oh, actually, yeah, we do need to stop screen sharing before we can do the Q&A.
Okay. All right, I'll do that. It's stopped.
Okay, so there we go. Okay, and again, for those kind of listening, there's a little dialog box in the top of your screen. If you're on the web platform of this, you can enter your question there, and that's what we're going to walk through. So if you have any question as we're going through this, please enter them there, and we'll just go through in the order they were received. And yes, Wally, we did get your question. It's kind of last on this list, so we'll get to that one as well. Okay, so first question here, is this work sponsored or funded by the U.S. government? And if so, do you have a POC organization you can provide?
Okay, actually, I will call on my program manager, Matt Neidig. Matt, can you help us out?
Sure. So the concept generation of Viper spawned from an NSC project that we did in support of DSO. At the end of that project, it was specifically tailored to modeling clutter environments in disparate environments themselves, so urban, rural, and suburban environments. At the end of that project, so that project essentially started by concluded by stitching together 3 disparate propagation models that did like 2D, and a 3D model. The result of that, at the end of that, we had a lessons learned discussion and came to the conclusion that that really wasn't a sufficient path forward for modeling these complex environments in the speed at which we needed and the accuracy in which we needed. As such, the movement towards Viper came from that NSC contract. It was with Defense Spectrum Office. The POC for that previous one, that Clutter project. Actually, I'm not positive I can mention his name here without checking with him, but it was out of the Defense Spectrum Office. I'll follow up with him, get it posted here if possible. But the development of Viper itself is not under that same government organization.
Thank you, Matt.
Great. Yeah, thank you. Any more you want to add to that, Emma?
No, we're good. So next.
Okay. Next question. All right. So can voxel properties be extended to include surface reflection and atmospheric characteristics for use in Earth to space or space to Earth analyses?
Yeah, I'll jump in here. This is Ed Smith-Rowan. Yes, basically we will have large voxels basically for an atmospheric refractivity model. Obviously you want, for a surface voxel, you, in addition to the normal and the curvature information, you want the material, from which you can derive a reflection coefficient. But yes, we definitely, have a large voxel for the atmospheric model, essentially. So we can account for refractivity and things like that. And atmospheric absorption, dispersion, things like that. Troposcatter also. Basically reflecting off of turbulence, essentially. So we'll have that in our model. Okay.
All right. Yeah. Thank you, Ed.
Sure.
Yeah, the next question is an easy one. So here we go. Can you spell out Viper acronym again?
Sure. I had a hard time myself to remember it, but it stands for volumetric integrative propagation engine for ray tracing. Okay.
There you go. Very good. Got them all. Okay, next question. Does the tool handle multipath and greater than first and second order propagations?
Yeah, I'm back on Ed Smith-Rowan here. So yes, we will handle multipath, and multiple reflections and diffractions will probably have a user specified upper limit, like 5 reflections or something. After a while, it becomes both high loss and higher uncertainty. But yeah, definitely, we need to treat several events along a path. Basically, what the user will provide regions of voxels to receive and collect information, and all the rays that bounce in or diffract into a given voxel will be accumulated in a total field. We're doing the vector sum of the fields, and then putting an antenna in there, for example, and presenting, either a current or an aperture field to an antenna to collect the result, or you can just look at the field. So there, yeah, that's okay.
Perfect. All right, that works. Let's jump to the next question here. How can we access the material database that I guess you would have mentioned in the presentation here, and is it open source?
We're still working, quite frankly, on the API. I would have to go, whether this database is open source or not is above my pay grade, probably. We did get it from published papers, although we do have an experimental lab. A lot of it came from papers, IEEE papers and other papers that have, semi-analytic models and the parameters that go with them. Could probably point you to those open sources. But yeah, that's a good question. Yeah, it's
okay.
Yeah.
No, that's fine. So it sounds like there's not a particular database you use. You just use a variety of different sources to gather material information.
Yep.
Okay. Fair enough. All right. Next question. Can you discuss how you validated the model results, or did you, I suppose? And then have you compared estimates to the measured results, and in what scenarios?
So we're actually in the V&V phase right now. And Ed, do you want to go into details of how exactly we're actually conducting our model-to-model V&V as well as measure data?
Yeah, basically we have we're collecting scenarios that would overlap with our other models. Say TIREM, for example, a terrain propagation model that does knife edges over the convex hull of the terrain. So basically, we set up rasters, add buildings to it, can run with Viper, run with TIREM, and compare results. We're in the middle of that right now. Also, we've done, collected drive test measurements, over several, like Baltimore and
So let me add to that answer.
Yeah, go ahead. Yeah.
So that NSC project that I mentioned earlier in support of DSO had both drive tests as well as airborne flight test data that were feeding into the model to validate the results of Viper versus the measured data and the result of stitching those other models together. Separate from this webinar, we can share results of that. If you want to reach out to either Emma or Jen from those sections, we can talk about that.
Okay, that works. All right, next question. So can you simulate multipath propagation for GPS signals in urban canyons?
That is definitely a hope. I mean, basically, we're doing this ray tracing, so you should be able to put an antenna, either receiver or transmitter, down in buildings. I mean, we've all experienced, at least I've experienced, coming out of a parking garage, and my location being misapplied, when I try my GPS. So definitely, multipath in that environment towards a satellite is definitely a goal, and there's, that should work. Let me put it that way. We haven't tested that yet, but that should go.
Good, very good. So yeah, in theory, it's ready for that. You just gotta.
Yeah.
Okay. All right. Next question. So most ITU models are only valid up to 40 gigahertz. What models do you use above those frequencies?
Yeah. So basically, we would go to like a physics model, like propagation through dust. There are these knee series and the more simplified versions of those. That's all. Given the materials properties, if you've got epsilon and mu, complex, we'll just plug that into the physics models. And see what you get. Given a density and particle distribution, you should be able to get an estimate, of propagation effects. Yeah.
Okay, got it.
I hope that got it.
All right.
Yeah.
Yep. No, that's good. Next question. So, is the building surface roughness? Oh, did you? I'm sorry. Did you want to add to that? Anybody else? No. Okay. All right. The question is: building surface roughness one of the potential attributes of a voxel? And if so, are you able to account for diffuse scatter in urban scenarios?
Yeah, that's a good question. There's like a, if you have like a sigma roughness, parameter, there is a function that allows you to modify the reflection coefficient. We do that. We can do that. We haven't addressed like gratings or things like that. That could be a challenge, but I mean, certainly the voxel can be loaded with all sorts of stuff. As our modeling capability grows, we can certainly apply, certainly roughness is relatively easy, and things like corrugations could come later.
Okay.
Yeah. Okay.
All right.
Oh boy, my guess. Hold on. I'm gonna. Sorry.
All right. Well, let's see if I can answer this next question with or without Ed here. So, is Viper the next incarnation of the terrain integrated rough earth model, TIREM?
Yes, it is.
There you go. That was an easy question then.
So
right.
let me add a bit to it. So TIREM is a 2D model. The physics that TIREM has embedded in it has been extracted for use in Viper. The extension into the 3D space and the ray tracing is the next generation of that a similar analysis.
Okay, got it. That's a good addition.
Thank you, Matt.
Okay. All right, this is actually our last question, unless anyone wants to get any more in queue. But here it is. For those who would, or well, could not let in the presentation. Oh, here we go. I'll answer this one. Sorry. So for those who couldn't get into the presentation, the question is, how can you access what we've been discussing today and all? The answer, if you are still on here and can't get the presentation, is that first it's on our website, so DSIAC.org. And you can find this webinar, the web page for this webinar there. Grab the slides, the PDF version of the slides directly there. Alternatively, we'll be putting this recording onto our YouTube channel and Facebook page. So we'll be sharing out that information after today. Emails should go out this evening and later this week. It should be trickling out. So if you don't get that, you can find it on our website where you get access to that recording as well. And then, of course, Emma had put her contact information at the end of the slides there. So you certainly can contact Emma to get more information about this presentation or anything else and kind of go from there.
Yeah, either just email me or Jen Super. One of us will get to you as soon as possible. So thank you.
Yeah, perfect. Okay, well, great. I think we're just about here at the end of the hour and end of our questions. So Emma, Ed, Matt, appreciate you all joining in to help deliver this presentation, answer some questions. Thank you to everybody else who has participated in this so far and stuck it out all the way through. Again, if you have any questions, head to DSIAC.org. We can get you in touch with any of the presenters and or you can go directly to them as well. And we look forward to more. So thank you all.
Thank you, Brian. I really appreciate it once again.
Thank you all.